Yeah. Using the type allocation function. Right, so there was a list of pull requests.
Commits, more like
Commits, not pull requests, yes. On a branch.
ABI free.
Maybe 3. Should probably make that the main branch. And this was it. Use the type allocation function. So let's skip this one for now. Go back to adding the runtime Python version. And let's go first to the convert to GC objects. And then come back to the type allocation function. Okay. So GC objects. Python has two types of objects, GC and non-GC. That stands for garbage collection. The non-GC objects are simpler, but they cannot participate in reference cycles, right? So
sorry, by reference cycles you mean like incref decref thing?
By one object referencing another, and that other object referencing the first one back.
Okay.
So very simple objects like tuples, well, not tuples, well, strings that don't reference any other Python object at all would be non-GC, but pretty much every other object is a GC object. Let me open. I don't have my drawing here. So the problem with non-GC objects is that when you have dynamic type objects, not the static but the heap types, each object has a reference to its type, and the type can have a reference to its module, and the module is, well, has a namespace that anybody can change. You can add attributes to a module, so you can create a reference back to the object, right? So with heap types, it's very hard to have non-GC objects. Basically, it's probably possible, but it would be hard to basically make sure that all the invariants are followed. So that means usually when you switch to heap types, you need to make those heap types GC objects. How is that done? The type needs to have the PyTP flags have GC flag, which adds some new fields to the object structure, or pre-header or whatever. There must be a visit function that must visit the type on the object on Python 3.9 and more, because earlier versions had a bug. I don't know if 3.8 is still supported. If not, then we can remove some ifs. And also the deallocation function must call PyObject GC untrack and remove a reference to the type. Right, I mean, a lot of this Python could do automatically, and if I have had unlimited type, I would make it so, but right now it's a bit complicated. So where do we start? Maybe let's start with some of the type changes. So at the very end of this, there's a spec for rpm. Type spec for rpm.spec. So we add the PyTP flags have GC to the flags there. Right, that's the easiest one. We also add a traverse function to the spec, and the traverse function will visit the type if the Python version is big enough. Okay. Then to the dealloc, we add the PyObject GC untrack, and we get the object's type, get the object's free function. So this is TP traverse, TP doc, and so on. There's a type TP free. So we get that slot because we cannot get the TP free from the type itself and limited API. So there's a free function that will free the object. Right? And then we decref the type at the end. This is repeated about 100 times for all the types there are in this commit, and I don't think there are any other changes. So let me apply that. Test, and we have a bunch of failures. So let's see what those failures are. Build tests, RPM tests, dir 126 log, and what does this say? Exit code was 139, expected 0. Does it say anything else? No. Okay. So 127 also failed for me. Are you getting the same failures?
I have not tried it on my side.
Alright, so this also said exit code was 139. What is exit code 139?
Segfault?
Segfault! Yes. I expected that. So how can you tell? So Unix exit codes are 8 bits characters. So, and they're signed. So if you have 139 as a signed character. What's the Python way of doing this? Maybe array with like signed bytes, and we put in 139. Signed character is greater than maximum. Cannot do that. So unsigned character doesn't tell us much. Well, 139 should be hopefully the same as -11. And 11 should be the code for the segmentation fault. Where do we have a list of signals? So the function signal 7. Is segmentation fault. So -11 is 139, and usually when a program dies from a signal, it returns this exit code, and then the test suite interprets it as an unsigned character, so it gives you this high number. Right, so so something failed somewhere. Something accessed memory it shouldn't have. Let's see, the other failure should probably be the same thing.
That one is our test, so it's just but it also
that's the third one. Our test is probably still failing. 36. Oh, that's mine.
130.
130. Yeah, same thing. So that means this change did something wrong, and we should probably run GDB on this somehow and figure out where it went wrong. But since we're testing in a container, I'm not sure how to run GDB on that. Where does... So this is a detour to show how to debug problems, right? I'm pretty sure I know where the problem is because we just skipped a commit. That fixes it, hopefully. But we should probably look into how to debug this. So if I'm in _build, was something built here? Oh, there's RPM SO, but I probably cannot just use that, right? So if I do Python path equals Python and I run Python, can I import _RPM? No. That didn't work at all. Do I need to run GDB in a container? Is there anything interesting in the makefile we're using to run the tests? Where does make check come from anyway? Where did we learn that? The RPM person told you, right?
It comes from README in tests.
Tests.
Yeah, we had to run CMake first to make the make commands available, but it also has different commands like make at shell and make shell, which should allow us into the container.
Ah, nice. Okay. That's it then. Make shell. Ha ha ha. Okay.
Maybe we would like to. Oh, there is GDB headless installed in that container.
GDB headless.
Maybe we can also create a container with some more.
But it looks like I can import RPM. Which comes from user local site packages.
And I think the shared object was imported with rpm._rpm.
Oh. Ah, there we go. That's the one then. So if I now run test 126,
there is test py in the same directory. Maybe that would be cleaner. In the tree, you can see it. It's got like this yellow Python.
Oh, this one.
Yes. Yes.
Ah. Okay. No. RPM add macro. Oh, it was get env DB format. We don't need a DB backend, right? We don't even need myprint. Oh, we do need myprint. Okay, so next up, I'm using the old interactive console, which expects each function to be followed by a blank line. And there we go, segmentation fault. Nice. So, how to fix this? I will remove this DB backend so I can paste next time. Shouldn't have saved that. And I run gdb args python 3 command not found. Oh, does this container not have internet? Nice. There's nothing in this container. What do we do? What do we do? There's some kind of Docker file.
Yeah, we can add it to the Docker file. There is GDB headless. We can add just GDB. GDB headless is on line 51.
Okay, so let's do GDB. And we'll...
Do we want also to add Python 3 debug to get more information? I try to be smart, but I have no idea what I'm suggesting.
That's a good idea. I mean, GDB should download the debug information automatically once you allow it first, but since we don't have internet, that will probably not work. Yeah, and disabling the internet is not done within the container. That's probably expected. gdb args python 3 enable debug info d. Well, sure, but there's no internet, so now I run it with R. I couldn't find any debug info, but now I can put in this script and program received signal SIGSEGV segmentation fault from PyObject GC untrack.
That's the one we added to all those types.
Yes. And there's no source for this. Yeah. The debug info D would have helped with this probably, and installed also the sources, not just the debug info. But we can go up, and we see this is an RPM file dialog. In well, I don't see the file name here, but it should be somewhere in Python. RPM files. This is RPM files. We want RPM file. No. Where is RPM file dialog? Here it is. RPM files py.c. RPM file dialog uses PyObject GC untrack. So what's the problem here? Apparently PyObject GC untrack is the wrong thing to use somehow. This is RPM file type slots, which uses the TP dialog and sets it to dialog. Is the PyTP flags have GC? That's fine. But I see the problem already. There is a creation function called RPM file wrap. So in RPM, the functions that create the Python objects are usually called something wrap, because it wraps the internal RPM structure. Right. So with the wrap, you create the Python object, and this does PyObject new. Right. PyObject new says allocate a new Python object, blah blah blah, and either it's been fixed in the new version. No. Then I hope I have a pull request somewhere in flight to add a note here that if you have a GC object, you should not use PyObject new on it. You should use PyObject GC new. Right? Analogous to PyObject new, but for container objects with blah blah blah. You can see how the documentation is not very helpful in this regard. There should be a note here saying, you know, if you use this function on the wrong type of object, you'll get a sig fault and you'll never know why. So yeah, so this should use PyObject GC new. And let's make check. Yeah, and that fixes it.
Cool.
So PyObject GC new will create the necessary information for the garbage collector to work, which is then cleared in the GC untrack. But generally, this is not the function to use. If you want to create a new object, well, as a user of that object, you should call the type, right? That's the best way to create a Python object. But as someone who implements the object, instead of new, you should use a slot, and that slot is probably tpalloc. I hope. So these slots are somewhat confusing. There's tp new, which takes Python arguments. So that's almost the same as calling the type object. So you probably never want to call this one directly. There's alloc, and I don't know if there's any other new like one. There's init, which is like calling the dunter init. Probably never want to call that one for your own objects either. There's alloc new, yeah, free. There's a bunch of ones that destroy the object in various ways, but I think alloc is the correct one to use here. It uses PyType generic alloc, uses Python's default memory allocation mechanism. And that should, I hope, eventually called PyObject-GC_new or PyObject-new, depending on what type of object it is.
Mm-hmm.
So, instead of this function, PyObject-GC_new, you want to get that, so you would write something like alloc func alloc equals, so this is the type, right? So the type tp alloc, and instead of PyObject-GC_new, you call that function. And this is an alloc func, so it takes a class and the number of items.
Mm-hmm.
So it will take this class, and the number of items is 0 in this case. And the signature is a bit different. The GC_new is actually macro that calls that allocates the object and also casts it to this type. So if you call the function directly, the cast needs to be written like that, right?
How do you know items is 0 and what is items?
Items, okay. So some objects are variable sized. If you look at the PyObject-GC_new again, there's a variant called PyObject-GC_new var, which is analogous to PyObject-new var, and that one takes a size. And this is for objects like tuples that have a variable number of items that are allocated together with the object, right? So this is variable size objects that can't change their size after allocation.
Mm-hmm.
Since we don't have that, so yeah, the alloc function takes the argument, but for our purposes, we don't want to pass that argument. We set it to 0. I think it's also ignored. Right? So that would be the way, except there's one little problem. The type structure in the limited API is opaque. You cannot use TP-alloc like this. So you need some way to get that function pointer from the type object, and that some way is called a function called PyType getSlot. Right? So instead of doing this, like asking the C compiler to reach in at a specific point in memory, there's a name. So this is just a number, and we're telling Python, please give me this this slot, right? So there's some kind of indirection. We take a specific slot, and depending on the version of Python, it can be in different at a different offset in the structure. So this should hopefully work.
I understand this bit.
Right, nice. So hopefully this will work, and hopefully this will be same as the commit we skipped. Oh yeah, we get the type, we get the slot, cast it into the alloc function, which we didn't really do here because PyType getSlot gives you a generic function pointer, so the cast is automatic. Then call the alloc with the type and 0, cast that to silence the compiler, and yeah, that's it. So that's this commit.
Okay.
I hope you understand that now. Woohoo!
I kind of know what we did.
Great.
The underlying things are quite cloudy still, but
right. Well, if you figure out a specific question, I can of course answer it. Otherwise, well, let's just do more stuff like this and it'll become clear.
I don't have a specific question. It's a general question about types, like all those type things we are doing around types. It's just I think I lack some basics. But there's not a specific question there.
So Python types or the C types?
Those PyTypes.
PyTypes, okay.
Creating Python types, I guess.
Right. So of course Python types are the objects that act as types. Internally, they are Python objects. But some of them are static. So if we look into CPython, let's say longObject.c, there should be a pylong type, right? So this is a static C structure that is the type. So if you do like ID of some object, it'll give you a different kind of address than if you do ID of no.
Good.
Interesting. Okay. I might have some kind of memory randomization. This used to be different as far as I remember. Interesting. Anyway, so the int type is statically like wired into the Python binary. So this is it. That's the structure. It has some PyType. It has some header, and this is a pyvar object head init. Pyvar object is a very simple structure that has 3 fields, but it's not defined in a very simple way. So it has the size, which is just the number of elements, and it has ref count and a type. So it includes PyObject. So every Python object has a ref count and a type. Pyvar object has a size on top of that, because types are variable sized like tuples. Right, so there is that, and then it has a lot of fields with these names, and those describe the type. So there's a string here with the name, a complicated number telling you the size of the object. So for ints, there's some structure called pylong object, and that has a field called obdigit, and everything before that field is like the basic size of and like the minimal size of a Python integer. Then there's an item size, which is the size of each digit. Right, so the int object can have any number of digits, and this is the size of 1. Then there's a bunch of function pointers. So there's a deallocation function. So this is a function that gets called when an integer needs to be deallocated. This is a function that's called when you need to take the representation of an integer. That'll take the self and return a Python string. There are flags, so these are just bits that say you can derive other types from int. Ints are ints, so that's an optimization, and that's also an optimization. There's tpdoc, so this is a C string with the doc string, and so on. So everything about a type is just put in this struct.
Okay.
What we're doing in RPM is creating this structure dynamically, so allocating it on the heap. And that's because we don't have access to the layout. A new version of Python can, reorder this theoretically and do things like that, or add new stuff at the end. So we cannot just, declare it like this. We need to tell Python to allocate the proper amount of memory and then fill it in. So how that's done is using a spec and slots. So if we look here, there's RPM file type spec, which is a structure that's much more simple. And it has like the name and the flags in here, but the main thing here is slots, which is an array of a number and a pointer. And the number tells Python, the TP new member of the structure should be set of this, and the get arrow member should be set of that. And if Python ever gets rid of this this member, then it can just raise an error here. Or if there's a new member added to the type structure, we just define a new number. Right, so this is extensible. The array of slots is wrapped in a spec, which is like mostly historical artifact. These could also be slots. Right, and then somewhere in this helper function, we say pytype from spec. Give Python this static spec structure with the description of the type, and get back an actual type object. And then we add that to the module, and also save it in some place in the module state.
So in like Python's terms, what gets created is a class that can be used.
Yes.
Okay.
So type and class in Python are synonyms since Python 3. If you remember, in Python 2 there was a difference between creating a class like this and creating a class that derives from object. So and also way before that, the built-in types, the types that don't have an uppercase letter at the start, were a very different kind of object than the classes you normally create. So there was a difference between types and classes, but nowadays it's all the same.
All right. I think it gets clearer. Thank you for the repetition of
no problem. Thank you for the questions. Alrighty, so that was what we wanted to explain now, and I'm interested to see what happens next.
Okay, someone made me switched off the lights. I'm going to just try to make the night back a day.
Meanwhile, I'll look at what we're doing. Ah, okay.
Okay, Fiat looks, I'm back to the daily mode.
Alright, so next up, one interesting part about all the types, like we can look at long object again, is that there's this structure, like a C structure, that holds information for each object of that type. So the PyLong object structure will have, I don't know, the size of how many digits are there in the long, and the sign, and whatever. The RPM structs are this. There's RPM file object, which is probably defined in a header. No, it's not. So where is it defined? The start here somewhere. Oh,
is there? No.
Oh, there's the type def. So RPM file object is this structure. So all the other C files that include this header can work with RPM file object, but the contents of the structure itself are local to this file only. All right. So what does each RPM file object contain? That's the PyObject head, so the reference count and the pointer to the type. There's some mddict. There's an RPM thingy called files. So this comes from RPM itself. So it's some something that we're wrapping with this object, and there's some kind of index, right? So this is the actual data that's needed to represent whatever information this is representing. Right? This is Python's, this was what makes it a Python object. It has a reference count and a type. And this, I tried to figure out what this is. And in some of the headers it has a comment to look like PyModule object. So Python module objects apparently have a dict right after the Python object header, which is of course a CPython implementation detail. Like, you shouldn't rely on something appearing somewhere in the memory for an internal Python object. And if I grep for mddict, it's all the declarations, right? So in a lot of these files, let's just declare that. Let me add a bit more context. So after the PyObject head, there's mddict. Sometimes it's to look like PyModule object. This is never used anywhere. And if you cast an RPM object to a PyModule object, you will not get good results, to say the least. So I tried to explain that in the commit message. Remove blah 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 that were added in this commit from 2002. Add this line to all RPM foo types with like no explanation.
It kind of seems to me that maybe not even those are not all the types we have at the moment in RPM.
Yeah, maybe they're all. Maybe it wasn't added to some of the types. Yeah, so PyModule object internal structure is an internal detail. If we're using the limited API, we have no business trying to look like that. If you use some of these types as PyModule object, you'll run into trouble both with C, optimizing accesses to one or the other, and thinking those are separate. This is undocumented and unused. I wasn't able to find where it's used, what it's for. So off it goes, basically.
Mm-hmm. You are still in the... Oh no, you're not in the container. Sorry, I misinterpreted.
So hopefully that got rid of all of those. Okay, next up. Visit PyObject member and TP visit hooks. Right. So we made all of the object GC objects, which means they can participate in Python's cyclic garbage collection, and they can form reference cycles. But that also means they need to inform the Python's garbage collector about what objects are reachable from them.
Mm-hmm.
And for that we have the visit functions, and we've seen some of these already, I think.
Yeah, we talked about visit being a macro.
Traverse, right.
Traverse, yeah.
Right, so we've added all these traverse functions. There's PyVisit, that's the macro that takes an object and calls this visit function with the object and the arg. So far, all of these traverse functions, what they do is visit the type. What they should do is visit all the Python objects that are referenced from this RPM file object. Right? So in this case, there are no Python objects except the type, but in other cases, there are some, apparently. So RPM_II. RPM_II. So there's the head, and there's a reference for dbtc ref counting. What is that? I don't know. But this is a common technique where, for example, if this RPMDB index iterator needs a database object, we add a reference to that database object here, and that reference will keep the database alive as long as this object is alive, right? So if you cannot delete the database while this iterator that's using the database is still active, right? So that's why we have this reference, and whenever RPM_II is deallocated, the reference gets not deallocated, the reference gets decreased. So here we're saying the database or whatever it's referencing is no longer needed. Where is it set? In the wrap, in the constructor, it's set to some argument here, and it's encrypt. Right? In modern Python code, you would call py_new_ref, which is exactly like incref, but it has a return value, so you can use it directly like this. In old Python code, all we had was incref. Alright, so since we have the reference, we need to visit it in the traverse function. So that's what this commit does. Hopefully it does it to all the types that need it. There's a ref in RPM_II. There's a ref in RPM_I. I have no idea what those mean. And there are two things in RPM_TSPy. Right. How do you know if you need to visit something in traverse if you have any kind of Python object in the struct? Right? And since Python 3.9, that includes the type, which is a bit inconvenient. Right. What's next? Ooh, Use PyModule def slot and multi-phase initialization.
Oh, that sounds like something we want from the start.
Right. So, all right. So we talked about these type slots that we're now using. So the same thing we have for modules. So historically, extension modules were defined using this module def structure that says what the module's name is, what the docstring is, how much size it needs for its internal data, what the functions, like the global functions of the module are, and then how to get rid of the module. Like these are 3 function pointers. And right here there was a reload function that was never implemented, so this was always set to null. But then it became clear that we want to add more fields, like more information to the structure, but we couldn't because this has a fixed size and everybody was compiling with this structure. So how do you extend this? Well, we reused the unused thing and made it point to an array of slots, like with the type slots, right? So anything that wasn't in the original version of the module def is now in a slot, like numbered pointers.
Okay, so slots are basically a pointer somewhere, so it doesn't increase the size of the structure, but you can just add
they point to some other piece of memory. Yes.
Oh, that's clever.
Yeah, so that's like with the types here. So there's slots. You have that, right? By the way, what I'm working now on right now currently in CPython is getting rid of these spec structures and just using only slots because it doesn't really make sense to have fields in a struct that we can't deprecate. Anyway, let's go back in here. So there are slots, and we're already using slots.
Maybe we got to that this time quicker because we were just started working on that from a different angle.
Right, that makes sense. Right, so yeah, so this uses the slots. There was mreload before, like the reload function instead of traverse clear and free, and that never worked and was never implemented. Right, module reloading, no, that's that can't work, so that was null. And now it's an array of slots. This is some interesting, rather new C syntax, where instead of having the arrays separately like this, you can define it like that. So this looks like a cast. Cast to an array, and then the array is here. That's just C syntax. It means exactly the same thing as this, except now here you need a name, and it's spread all over the place. So we don't need to do that. This also does the PyModule def init, and returns the module def itself from the initialization function. Before that function created the module, initialized it. Now it just returns the module def, which has the init function in one of the slots. And the init function needs to return -1 instead of 0, so that's all the other changes. I think we already have that. Yes. Init module -1s. Ooh, there's a 0 here.
That may be an oversight.
Yes, that's an oversight, so let me fix that. Oh no, it's not an oversight. That came from an earlier commit here somewhere. So now we need to fix that. Let's see if we have more oversights like that. So all the returns are -1s. And at the end is 0. And register enum, hopefully. Oh, that doesn't have an error return, which is not great. Okay, so let's fix that return. Right, and next up will be using module state. So what this means is that we don't have a static module state like this. Where is this defined? This is defined statically somewhere. Here it is.
Yeah.
Right. A global static function. Well, a global pointer that is allocated once and never deallocated. And all the module objects that get created, like all the _rpm module objects, share that module state, which is why we cannot use it in subinterpreters. So this commit will, instead of using the global pointer, we'll use PyModule get state and get the module's memory. But that's for next week.
Okay, thank you.
Thanks for your attention. Let me push this. I don't know if you want to recreate it. So now I have a my multi-phase branch as well.
Okay.
How confusing is that?
Yeah, okay.
All right.
I'll make sure to fetch it later.
See you next week.
See you, bye-bye.